The National Electrical Code, Section 430.250 provides a table of full load current values for motors. However, this table typically stops at 500 horsepower. Attempting to extrapolate beyond the table's range is not an accurate approach to determining the full load current, often abbreviated as FLC, for larger motors. Instead, the National Electrical Code offers a formula specifically designed for calculating the full load current when the motor's horsepower rating is known. This formula is as follows: full load current equals horsepower multiplied by 746, all divided by voltage multiplied by efficiency multiplied by the power factor. Let's break down each component of this formula. Horsepower represents the motor's mechanical output power, typically found on the motor's nameplate. The constant 746 converts horsepower to watts, as 1 horsepower is equivalent to 746 watts. Voltage refers to the motor's rated voltage, also available on the motor's nameplate. Common voltage ratings for industrial motors include 208 volts, 240 volts, 480 volts, and 600 volts. Efficiency represents the ratio of mechanical output power to electrical input power, expressed as a decimal or percentage. The efficiency value can be found on the motor's nameplate. Power factor represents the ratio of real power to apparent power, indicating how effectively the motor uses electrical power. The power factor is also typically found on the motor's nameplate, expressed as a decimal. For induction motors, which are commonly used in industrial applications, typical efficiency and power factor values can be estimated if the specific motor nameplate data is unavailable. A reasonable estimate for efficiency is 90%, or 0.90 as a decimal, and a typical power factor might be 0.85. Let's consider an example. Suppose we need to calculate the full load current for a 2000 horsepower motor operating at 480 volts. Using the formula and our estimated values, we have full load current equals 2000 multiplied by 746 divided by 480 multiplied by 0.90 multiplied by 0.85. Performing the calculation, 2000 multiplied by 746 equals 1,492,000. In the denominator, 480 multiplied by 0.90 equals 432. And 432 multiplied by 0.85 equals 367.2. Therefore, full load current equals 1,492,000 divided by 367.2. This results in a full load current of approximately 4,062 amps. It is crucial to note that this calculated full load current value is essential for several electrical design considerations. Firstly, conductor sizing. The conductor supplying power to the motor must be adequately sized to carry the full load current continuously without overheating. The National Electrical Code provides tables such as Table 310.15, B16 to determine the appropriate conductor size based on the ampacity or current carrying capacity of the conductor. Secondly, overload protection. Overload protection devices, such as thermal overload relays or electronic motor protection relays, are designed to protect the motor from sustained overcurrent conditions that could damage the motor windings. The overload protection should be sized based on the motor's full load current, typically set at 125% of the FLC for motors with a service factor of 1.15 or greater, or those with a temperature rise not exceeding 40 degrees Celsius. Thirdly, short circuit and ground fault protection. Short circuit and ground fault protection devices, such as fuses or circuit breakers, are intended to protect the electrical system from high-level fault currents that could occur due to short circuits or ground faults. The sizing of these devices must consider the motor's full load current and its starting characteristics. In addition to full load current calculations, understanding motor starting methods is crucial, especially for large motors. Large motors can draw significantly higher current during starting than during normal operation. This high inrush current can cause voltage dips, potentially affecting other equipment connected to the same electrical system. The utility company may impose limits on the allowable motor starting current to prevent such disturbances. Given a utility company's starting current limit of 2400 amps at 480 volts, Motors exceeding 1000 horsepower would likely exceed this limit if started using a full voltage starting method, also known as across-the-line starting. Full voltage starting applies the full voltage to the motor terminals at startup, resulting in a high inrush current, typically 6 to 8 times the full load current. To mitigate the high inrush current associated with full voltage starting, reduced voltage starting methods can be employed. These methods reduce the voltage applied to the motor during startup, thereby reducing the inrush current. Several reduced voltage starting methods are available, each with its advantages and disadvantages. Firstly, autotransformer starting. An autotransformer is used to reduce the voltage applied to the motor during starting. The autotransformer has multiple taps, allowing for different voltage levels to be selected. Once the motor reaches a certain speed, the autotransformer is bypassed, and the motor operates at full voltage. Autotransformer starting provides good torque control and is suitable for applications requiring high starting torque. Secondly, reactor starting. A reactor, which is an inductor, is placed in series with the motor during starting to limit the current. Similar to autotransformer starting, once the motor reaches a certain speed, the reactor is bypassed. Reactor starting is a relatively simple and cost-effective method, but it provides less torque control than autotransformer starting. Thirdly, part winding starting. Part winding starting is applicable to motors specifically designed for the starting method. The motor windings are divided into 2 or more parallel circuits. During starting, only a portion of the windings is energized, reducing the inrush current. Once the motor reaches a certain speed, the remaining windings are energized. Part winding starting is a simple and inexpensive method, but it provides limited starting torque and is not suitable for all motor types. Fourthly, Y-delta starting. Y-delta starting is another method applicable to motors specifically designed for the starting method. During starting, the motor windings are connected in a Y configuration, which reduces the voltage applied to each winding. Once the motor reaches a certain speed, the windings are reconnected in a delta configuration, applying full voltage to the windings. Y-delta starting is a commonly used method, providing a good balance between starting torque and current reduction. Fifthly, soft starters. Soft starters use solid-state devices, such as silicon-controlled rectifiers, to gradually increase the voltage applied to the motor during starting. Soft starters provide smooth and stepless starting, offering excellent control over the motor's acceleration and deceleration. Soft starters also offer advanced protection features, such as overload protection, under-voltage protection, and phase loss protection. Considering the utility company's starting current limit of 2400 amps, reduced voltage starting methods such as autotransformers or soft starters would likely be necessary for motors in the 1000 to 2000 horsepower range. The specific starting method chosen would depend on factors such as the application's torque requirements, the motor's design, and the cost considerations. When selecting a motor and its associated starting method, it is essential to consult with a qualified electrical engineer and the utility company to ensure compliance with all applicable codes and regulations and to ensure the reliable and safe operation of the electrical system. Furthermore, a motor selection based on the calculated full load current, or FLC, can be further optimized when combined with other considerations. Firstly, service factor. The motor's service factor indicates the amount of overload the motor can handle for short periods without causing damage. A higher service factor allows for greater flexibility in handling temporary overloads. Secondly, motor efficiency. Selecting a high-efficiency motor can reduce energy consumption and operating costs over the motor's lifespan. Premium efficiency motors, also known as nano-premium motors, meet specific efficiency standards and can provide significant energy savings. Thirdly, enclosure type. The motor's enclosure type should be selected based on the environmental conditions in which the motor will operate. Open drip-proof enclosures are suitable for clean and dry environments, while totally enclosed fan-cooled enclosures are suitable for dusty or wet environment. Fourthly, insulation class. The motor's insulation class indicates the maximum operating temperature of the motor windings. Higher insulation classes allow for higher operating temperatures, providing greater thermal protection. Fifthly, bearings. The motor's bearing should be selected based on the application's load and speed requirements. Ball bearings are suitable for most applications, while roller bearings are suitable for heavy-duty applications. Sixthly, vibration. Motor vibration can cause premature wear and failure. Selecting a motor with low vibration levels can improve reliability and extend the motor's lifespan. Seventh, altitude. The motor's altitude rating should be considered, especially for motors operating at high altitudes. High altitudes can reduce the motor's cooling capacity, requiring diluting of the motor's horsepower. Eighth, ambient temperature. The motor's ambient temperature rating should be considered, especially for motors operating in high-temperature environments. High ambient temperatures can reduce the motor's cooling capacity, requiring diluting of the motor's horsepower. Ninth, harmonic distortion. Harmonic distortion in the electrical system can cause overheating and damage to the motor. Harmonic filters or reactors can be used to mitigate the effects of harmonic distortion. 10th, power quality. Poor power quality, such as voltage sags, swells, and transients, can damage the motor. Power quality monitoring and mitigation equipment can be used to improve power quality and protect the motor. These considerations, combined with the accurate calculation of full load current and the appropriate selection of a motor starting method, will contribute to a reliable and efficient motor installation.